Hello, everyone. I am very glad to introduce our paper Aether. To begin, let's quickly recap the concept of a world model. At its core, a world model aims to learn the transition function of an environment. That is, given a certain state and an action, it predicts the next state. When we construct a world model, there are several critical factors to consider. First, we need to define a clear action space. Second, the model must effectively handle state estimation to understand the world around it. Third, our priority should be transition authenticity, ensuring the predicted changes are physically plausible rather than just creating visually pleasing, or aesthetic, results. And finally, the model must be scalable, capable of learning from massive datasets, both from the real world via the internet and from simulated environments. This brings us to Aether, a unified framework designed to address these challenges. Aether integrates three key capabilities into a single model. First, action condition prediction. It can predict future video frames based on an initial image and a specific camera trajectory. Second, visual planning. It can generate a plausible path between a starting observation image and a final goal image. Third, 4D reconstruction. It can reconstruct dynamic 3D scenes from videos by estimating both depth and camera poses over time. Now, let's see how Aether tackles the key factors we just discussed. First, for the action space, Aether makes a very effective choice. It uses camera pose as a unified and simplified action space. This is powerful because in first-person navigation tasks, the camera's path is the agent's path. In robotics, the motion of a camera on a robot's hand can directly represent the 6D movement of the end effector. Next, to handle state estimation, Aether incorporates both reconstruction and generation within a single multitask learning framework. By training the model to simultaneously generate video and reconstruct the underlying 3D geometry, like depth and camera pose, it develops a much richer and more physically grounded understanding of the world state. How do we ensure the model learns authentic, realistic transitions? Aether achieves this by incorporating visual planning directly into its unified framework. By requiring the model to generate a believable sequence of frames to connect a start and goal image, we are implicitly teaching it the rules of how an environment can realistically evolve. To be scalable, Aether doesn't start from scratch. It builds on the foundation of a powerful, pre-trained video generation model. This allows it to leverage the vast visual knowledge already learned from diverse, internet-scale data, giving it a significant head start. And for scalability with simulation data, Aether uses a clever strategy. It uses geometry as a bridge between the simulated and real worlds. While the visual appearance of a simulation might differ from reality, the underlying laws of geometry and physics are the same. This focus on geometry is the key to achieving robust sim-to-real generalization. This geometry bridge is effective because geometry has a very small sim-to-real gap. Previous works like Marigold and Depth Any Video have already demonstrated that diffusion models fine-tuned on synthetic data can generalize incredibly well to real-world depth estimation. Aether builds directly on this proven concept. To create the necessary training data, we developed an automatic annotation pipeline. This pipeline takes RGBD synthetic videos, for instance, from high-quality video games, and processes them through several stages. It first masks out dynamic objects, slices the videos into coherent clips, performs coarse and then refined camera estimation, and finally outputs fused 4D point clouds with precise camera annotations. Here we can see some examples of the data produced by the pipeline. These are high-quality, dense point cloud reconstructions from the synthetic videos, which serve as the geometric ground truth for training Aether. Let's look at the model itself. Aether is a multitask 4D video diffusion model. The core idea is to train it to denoise a latent representation that jointly encodes RGB, depth, and camera motion. We can guide the model to perform different tasks simply by changing the conditioning information. For 4D reconstruction, we condition on the full RGB video. For action-conditioned video prediction, we provide the first RGB frame and the whole camera action sequence. For visual planning, we condition on the first and last frames. To feed geometric data into the model, depth maps are first converted into disparity. This disparity is then normalized and replicated across 3 channels to match the input format required by the pre-trained video VAE, before being encoded into the latent space. camera trajectories undergo a similar process. The camera's translation is scaled and normalized. Then, this is used to construct a 6-channel ray map that encodes the origin and direction of camera rays. Finally, this ray map is downsampled to match the dimensions of the model's latent space. The model is trained on video clips of variable lengths and frame rates. Conditions are randomly masked during training, which enables the single model to learn all tasks simultaneously. The training itself is a 2-stage process. The first stage is standard latent diffusion training. The second stage refines the output by decoding it back to the image space and applying specialized, perception-based losses, such as MSSSAM for RGB and a scale-invariant loss for depth. Now, let's look at the results. For zero-shot video depth estimation, Aether achieves state-of-the-art or highly competitive performance on standard benchmarks. This is remarkable, as it was trained only on synthetic data and is generalizing to these real-world datasets. Similarly, for zero-shot camera pose estimation, Aether's performance is comparable to specialized feed-forward methods. This is a strong result for a unified, generative model that isn't solely optimized for this specific task. Here are some qualitative visualizations of the 4D reconstruction. The model is generating dense, coherent point clouds for these real-world videos. Again, it's crucial to remember this is all zero-shot generalization. The model never saw real-world data during training. In generation tasks, Aether was compared against its base model, CogVideoX. The results clearly show that Aether outperforms the baseline in both action-free and action-conditioned video prediction. This confirms that the specialized training on 4D synthetic data significantly enhanced its ability to generate controllable and realistic motion. These video examples demonstrate Aether's action-conditioned prediction. Given a starting image and a camera trajectory, the model generates a plausible video that accurately follows the specified motion, showcasing its fine-grained control. Finally, in visual planning experiments, Aether's abilities were put to the test. The tables show strong quantitative results. Most importantly, an ablation study was conducted where a version of Aether was trained without the depth objective. The planning performance dropped significantly, proving that explicit 4D geometric modeling is crucial for effective planning. Here are some fascinating examples of action-free visual planning. Given only a start and a goal image, Aether generates the intermediate frames, effectively planning a coherent path through the environment. This highlights its potential as a world model that can reason and act as an agent. Of course, no model is perfect. Aether has some limitations. Camera estimation is less accurate than depth estimation. Its performance is weaker on indoor scenes, likely due to a data bias towards outdoor environments in its training set. It can also struggle with generating highly dynamic scenes and, in its current form, does not incorporate language prompts. To conclude, Aether represents a significant step forward in building unified, geometry-aware world models. By synergistically integrating reconstruction, prediction, and planning, and by using a robust pipeline for synthetic data, it achieves impressive zero-shot generalization across a range of complex, real-world tasks. Thank you for your attention.